This video is sponsored by PCBWay. Welcome everyone. In this video I'm going to show you my newest project. As you can see, it's here on the desk and it looks like a camera because it is a camera. And I will show you how this thing works, and I will also show you what are the steps that I need to do, because it's not entirely ready. It works, it can take pictures, but I still have some things to do to make it into, for example, a totally mobile camera. Because now, as you can see, it has two wires here. One is a USB cable for connecting it to a computer, and another one is a DC jack, which is used to connect it to a power supply. And the reason why I need to connect it to a computer is because I received the image from this camera on the computer and I have to process the image there, because it's not directly a JPEG or a BMP file, but it's just a huge matrix. And then the power supply is needed because it has a stepper motor. But without further talking about this thing, let's see what is inside this box. So this is the camera, and it's a very funny concept, at least in my opinion, and I will explain everything, how this thing works and what are the main components, what does what, and so on and so on. So as you might remember, I showed this PCB in some of my other projects. For example, I built a spectrometer, and then the same PCB is here. You can see the TCD 1304 linear CCD right in the spectrometer, and that is the exact same PCB here with the TCD 1304 CCD and with the auxiliary circuit right here. And then it's connected to the same microcontroller, as you can see, STM32F401. And then there are some other components here. So as you can see, this is on some kind of holder. Maybe from sideways you'll see it better. And then this holder is on a miniaturized linear guide. I will try to find another part of this and I will show you from a closer perspective. So it looks like this. And I bought this thing specifically for this purpose. It took me quite some time to find this from a European seller, because I did not want to buy it from China, for example, from AliExpress, because it would take maybe a month or more to buy it. So I found a European company, and then it was with me within a week. So that's very nice. So I have this linear rail with this smaller carriage, and then this linear rail is moved back and forth with this NEMA 8 stepper motor, which has a built-in lead screw with a polymer nut. And this lead screw has 1 millimeter lead, which means that when the shaft turns one full rotation, then the linear displacement along this lead screw will be 1 millimeter. And then the motor is driven by a easy driver stepper motor driver, and then basically that's all. So now if you put together these things that I told you, you can guess that this thing is basically a scanner. And yeah, there are some projects on the internet, but I haven't seen any projects based on this CCD built from scratch, because all of the projects I found, just to have some ideas how the mechanisms are implemented and so on, they are just disassembled scanners, but this is built from scratch. So I wrote the code totally from scratch, as you could see it in some of my old videos, for example, how to drive this CCD, or how to work with this spectrometer and so on. So I know how to work with this CCD in and out, and I wrote my own software from scratch to drive it. And then I also wrote some simple code just to synchronize the motion with the reading and the transmission of the data to the computer. And then everything is basically works in a following way. When I send a command to the microcontroller, then the microcontroller starts to move in a certain direction. I made a cheat sheet for myself here, and it does a certain amount of steps, and then it takes a picture, which is basically just a line of pixels, sends it to the computer, and then steps again, a certain amount of steps, takes a picture, and so on and so on. And it does until the full frame is basically scanned. So the soul of this system is basically this PCB with the TCD1304 CCD and its circuitry. And then that is basically, which I told you earlier, it's based on this tiny PCB. And this PCB is provided by the sponsor of this video, PCBWay. PCBWay is a service provider specialized on PCB manufacturing, PCB assembly, but they also have other useful services such as CNC machining or 3D printing. And now it's especially important to visit their website because they have their 5th PCB design contest, where you can participate by sending your design to one of their 3 categories. And by participating in their competition, you can win valuable prizes. So please visit PCBWay.com and check their services and their 5th PCB design contest. So I hope you found PCBWay services interesting and you will use them for your next project. So coming back to this CCD, I want to discuss a little bit about this because it's the soul of the camera. So first of all, this camera is a full frame camera, which means that it can capture a frame of 35 millimeters along the horizontal axis and 24 millimeters along the vertical axis. And I chose the CCD to be parallel with the vertical axis because the sensitive area of this CCD is 29.1 millimeters. So then I can cover the 24 millimeters perfectly with this CCD. And we should know that 1 pixel is 8 micrometers high if you look at it on this direction. So it means that if I cover 24 millimeters with 8 micrometer step size, then I get 3000 pixels. So the vertical resolution of this thing can be 3000 pixels, which is quite neat. I would say it can compete with regular cameras. And then it comes the more difficult part, which is the horizontal resolution. And 1 pixel of this thing along the horizontal direction is 200 micrometers wide. And just to remember, we have to cover 35 millimeters along this direction, the horizontal direction. So if I, for example, calculate the step size based on the pixel width, then I have to divide 35 millimeters by 200 micrometers, and that is 175. So if I just move with the pixel width along the horizontal axis, I can only capture 175 full pixels, which is a very poor resolution. So I will divide them into smaller pixels or smaller steps. And that will mean actually that like adjacent pixels will overlap, like physically overlap based on the dimensions of the CCD or the pixel of the CCD. And how I do that is I start actually from the stepper motor. So this stepper motor and the shaft attached to it has 1 millimeter lead, and the stepper motor needs to do 200 steps to do a full turn on this lead screw. So 1 millimeter is 200 steps. So the 1 millimeter can be divided up to 200 equal parts, which means that the step size, the theoretical step size, will be 5 micrometers. So if I do one step with the stepper motor, which is 1.8 degrees rotation with this shaft, that will move the nut or this wall mechanical thingy along the horizontal axis by 5 micrometers. And then if I do the math again and divide 35 millimeters by 5 micrometers, that will give us 7,000 steps. So then with that, theoretically, I could have 3000 times 7000 pixels which is 21 megapixels, which is in a full frame system, it's quite nice, I would say. But I don't trust this mechanism here to be able to consistently do 5 micrometer steps. It's just a too simple system for that, and it's mounted on plastic and so on, and 3D printed parts. But I say, okay, let's do as a first approach a 10 times larger step size, so 50 micrometers step size. And then of course the number of steps on the horizontal axis will be 10 times less, so 700 steps. So I will have a very good resolution on the vertical axis, which is still 3000 pixels. And then on the horizontal axis, I will have only 700 pixels. So that's what I will use for now. And actually this is almost like the final version of this thing. You can see that this is mounted on a plate, and I drew everything in Fusion 360 to know the dimensions and everything, and then I designed this plate based on a simple plastic box, which you can see here. So this is a normal, like a hobby electronics box, and then I discarded this part. I mean, I did not throw it away, but I did not throw it away, but yeah, I did not need this. And then I have this. And luckily we have all the dimensions for this box, and that will be very important for a following reason. So when you have a camera, then the lens has a specific property or characteristics, and it is called the flange distance. And the flange distance is basically, if I simplify it, the distance between the end of the lens until the surface of the sensitive area, which can be the CCD or can be the film, the negative, if you use some older cameras. And that distance is very important. This is an M42 lens, so you can see the thread here. I use M42 because I could salvage this from an old Zenith E camera, and I have plenty of M42 lenses, so I used one here. And coming back to the flange distance is that this distance, so between here and the end of the, let's say, the path of the light, is very important because the light is focused properly on the surface of the sensor if the flange distance is set up properly. And also we have this scale, the focusing scale, that will work only if the flange distance is set up properly. And I have to talk about something here because it's very important that if you mess up the flange distance, two things can happen. If for example, for the M42, it is 45.46 millimeters. If you happen to increase this distance, so for some reason this tube is too long, then when you turn the focus ring to infinite distance, then the image back here will be focused in front of the sensor. So you will never reach a focused image on the sensor itself by turning the focusing ring at infinity because the geometry is just messed up. And this is actually a common thing if you try to use an M42 lens on a Nikon DSLR, because the Nikon DSLR has a somewhat longer flange distance than the M42 lenses. And because of that, if you just mount the lens on the Nikon DSLR, then at infinite settings with the focusing ring, the image will be blurry. You will not get a sharp image. And to do a correction for that, you can buy an adapter which not only allows you to mount the M42 lens on a Nikon DSLR, but it has a glass element, and that glass element is a dispersive element, so it scatters or disperses the light, so it makes it possible that the flange distance difference is corrected. But here I tried my best, but I did some trials, and of course the distance is not perfect, but I made this a little bit shorter than it should be. So that's fine, because I can reach the infinite settings, but my focusing scale will not be correct. I just wanted to mention this because this is very important, that when you build these kind of things, the distance between the end of the lens and the surface of the sensor is extremely important. And also there is a catch, which you can see in the datasheet of this CCD, that actually you have the sensor beneath the glass, which is obvious, but it's like deep down there. So there is a few millimeters, or maybe just a fraction of millimeter from this surface, that you actually have to consider when you try to build a system to have the perfect flange distance. And then, as I said, this thing is almost the final piece, but I had several iterations, and previously I tried to use this kind of small stepper motor, but then the problem is that it's not strong enough to deal with this kind of mechanical resistance, which is like acting on the shaft of the motor. So this linear guide, this guy here, is too stiff. As you can see now, it's not moving, so I really have to move this with some force, and this motor is just not strong enough. But initially I did this kind of frame where I actually had the motor. I will show you very quickly. So the motor was sitting here, like upside down, and then I had this plastic thing on top. So yeah, I try to make it work. So it was clamping on the motor, and then there is one steer shaft here, and there was another steer shaft here. So this center piece, this guy, could slide up and down. It was moved by this plastic thing here. And then now I disassemble this, and then this plastic part was mounted against this thing here, and then it held the lenses, or the lens, so one piece of lens, of course. And then it worked, but this was not the best mechanical construction, but I could make some quite okay image. I put an example on my website as a picture, so check the link in the description and check my website. But of course this cannot be, let's say, a permanent solution, because I don't find it very precise, and yeah, for proof of concept it was fine. And then I built another frame, and then here you can see here these four I don't know how to call them, pins, and they are actually holding this motor here. So you can see that it holds there, so it's for positioning. And then this thing was created for it. So this was holding this miniature PCB, and then this was sitting here, something like this, as you can see. And then it was scanning in this area. And then you can see that here is the counterpart, which is the tube for the lens. But this was also not the best, because when the motor moved this plastic part, then there was too much friction on this side. So it was a little bit always like at an angle, and it was not perfect. So then I tried a third version, like mounting the PCB directly on top of this plastic part. But this was also, again, just not perfect. It was a bit wonky, and it was not moving perfectly. It was lagging. So this motor is, of course, not powerful enough. So then at the end, I came up with this solution. And then what I will do after I finish with the, let's say, prototyping, is that this panel will be made out of a PCB. And then that is very good, because it's definitely stiffer than this thing. It's fiberglass, so it will be better than this 3D printed PLA. And I can directly mount the circuits on it, so I can wire everything on the back panel. And then also the back panel on this side will have a screen, it will have a few buttons. I will also have a shutter button on the top of this box, and then the system will also have a battery, SD card slot and everything. So that will make everything very portable and mobile, let's say. So this is now just the proof of concept which works at home, but it's not perfect enough to take it out on the field, but that's what I want to do at the end of the day. So now this just shows that the thing works, but then I will want to show that this thing works outside without any computer support and so on. So now I want to head to my computer and take a picture so you can see how this thing works, and I can prove that it works. And then I can explain how the image acquisition works, how the image processing works, and then how we should progress from this status further. So let's go to my computer and let's see how this thing works. Okay, so now what you can see is just the software, which is called QTIplot. And then why I use this is because the matrix, which is created by my software, is then imported into this software, and I can plot the matrix as an image very easily. So I just use this to create the image. But to create the image, I will use the same software I used to show you that I can capture the data from the CCD. So I just first connect the camera to the computer. And now things might be noisy because the stepper motor is quite noisy, especially in this box, because the box kind of amplifies the noise of this whole thing. But now the camera is hopefully directed at some object, and then I will try to take a picture of that object. I haven't played around with the focus too much. Actually, I haven't tested if the focus is properly set up. So the first picture might be a failure, but if we don't test, we never know. So I will start my software. So this is my software, and what we will do is I just connect to the COM4, which is the microcontroller, and then I just choose a relatively large integration time, let's say 2 milliseconds or maybe 3.7, and then I save it to a file. So this will save everything into a file. So let's start the acquisition basically. So now the scanning is going, as you can see, and probably here, and each of this line is basically one image. And you can see that there is something bright here, something dark here and here, and then here we are catching up with some kind of pattern, as you can see, as we scan. So this goes on and on until all the pixels or all the frame is scanned. And when that is done, I will stop this and we will plot the image and see what happens. Now you can see that this is getting flat and it's going down in intensity, which means that we reached the end of the frame. So I stop here. So now this is very low in intensity or bit value because the CCD is basically picking up dark areas. So that means that we scanned across the horizontal area. So then I will put this down on the desktop, and then I will drag and drop the file here. And then now you can see that it will import this kind of data. This is just a preview of a line, but then you will see that this is actually a matrix. It's a huge matrix, as you can see. So now I just print this. And I rotate the matrix. And I check the image again. And you can see that the image is kind of blurry, but I guess you recognize this girl. I will try to make this image a bit larger. So this is how the image looks like without proper focus. But it's not too bad. And maybe I will make another attempt just to make the image more focused. But you can see that it can take pictures at least, so we can kind of recognize the things. And yeah, it kind of shows what it should show. So we can capture an image. And yeah, you can see it's black and white, of course, because it's just a simple CCD without any color sensor or color filters. So it captures black and white. And what we did here is actually that each pixel here has a value. And that value is the intensity. And then this value is just translated into a gray scale value. And then it becomes a pixel, basically. And then you can see that that's what we see here. We might try one more scanning because I think it would worth it. So here is the software again, and let's capture another image. Let's see what happens. So again, you can see the intensity here and here. Now it's picking up some other object because this part moves. Here you see the drop, so something dark is here. Here something shiny, shiny. Again, here is a bright object. Then it's getting dark, as you can see, the intensity drops. So soon I can start this. Now it drops again, so this will be the end of the frame. So close this. So now, as you can see, the image got worse, so the focus is messed up. I can give it one more try, maybe. So let's try again. Done. Now it's a bit better, as you can see. So you can see the main object and then some other objects. Yeah, everything is on this tiny table. So yeah, the image quality is still not the best because you can see these stripes, and as you can see, it has some certain periodicity. So I guess that has something to do either with the stepping, maybe vibrations, or something with the way I read out the CCD. So I will check how that works, and I will improve that, obviously. And of course, the focusing is very difficult with this method. So I will try to do something about it. Of course, the best would be to have the perfect flange distance, and then I could rely on the focusing scale. So I could pretty much measure the distance between the object and the lens, and then set the focus distance to a proper position, and then yeah, that would work. But you can see that, for example, that the exposure is quite okay, I would say. So most of the things are really nicely exposed, and nothing is too dark or too bright. So at least that part works, but of course there is many things to improve. But some of these things mainly are like circuit design, for example, to make the PCB back panel. And then another part of the thing is programming, writing a better firmware for my microcontroller, which takes care of all the things. And now just to repeat it, so now we take care of the CCD reading, and we take care of the computer communication. So as you could see, I used my software to start the measurement, receive the data, and so on. So there is a communication between the microcontroller and the computer. And then the microcontroller also controls the stepper motor, because that's what moves the CCD. So that's how we do the scanning. And then what I want to add is a few buttons. Obviously a menu structure with the display, so I can see the image which I scanned and modify the settings and so on. And then I also want to add an SD card, so I can write the pictures on the SD card and maybe read them to check them if they were successful and so on. And then I will also add a few limit switches, so it will be easier for me to know when the motor arrived to the, let's say, finish and the start positions, and so on and so on. But the project works, as you can see. So I already have a good starting point, and most of the things are figured out, so I just need time to work on this. But I think that this is a very interesting project, and it involves a lot of things. So I will try to increase my knowledge in these areas to make this project better and better. So first of all, don't forget to visit my website, because I put a lot of information there. I wrote a small article about basically the content of this video and what was the work done behind the scenes and so on, how to do the calculations, and I also, as usual, put up some extra pictures. Also, don't forget to visit the website of PCBWay, and also through my project page on PCBWay, you can buy this tiny TCD1304 CCD driver PCB. So you can maybe build the same project and have fun with the camera that you built yourself. And yeah, it's a nice project and a challenging project, I think. So I hope you found this video interesting. I hope you learned something, and see you in the next video.